Welcome, viewers, to the third and the last segment of the third lecture for the online series of lectures for the course of Algebraic Topology 2. This segment is dedicated to the background materials required to understand the axiomatic approaches to homology theory. So let me start with exact homology sequence. Homology sequence. Here is the definition. Consider a sequence which may be finite or infinite This is a sequence of groups and group homomorphisms A1, A2, A3. So the group homomorphism from the abelian group A1 to A2 is phi1, and the group homomorphism from A2 to A3 is phi2, and so on. This sequence is said to be exact at the object A2 if image of this map phi1 is equal to the kernel of this map phi2. Okay, if it is everywhere exact, it is said to be an exact sequence. Okay, of course, exactness is not defined, at the two ends of a sequence if they exist. In other words, if the sequence is finite. Okay, now there are several useful facts about exact sequences that one needs to study very carefully. The proofs of these facts are left as exercises. Okay, several useful facts about exact sequences are listed below. The proofs of the facts are left as exercises, as an exercise. Okay, so one thing to note here is that since the groups of the objects of the sequence, right, or the groups that we are studying are abelian, we denote by 0 the trivial one element group, okay, where 0 is the identity element. Okay, let me write it here. Note that the groups under study are all abelian. And hence we denote by 0 the trivial one element group. Okay, so the first fact is that A1 to A2 to 0 is the trivial one element group. Okay, phi, this sequence is exact if and only if phi is an epimorphism. This means surjective. The second fact is 0 to A1 to A2. This map is given by phi, is denoted by phi. This sequence is exact if phi is a monomorphism. Monomorphism means injective map. Okay. Third fact is that suppose the sequence 0 to A1 to A2 to A3 to 0, where the group homomorphism from A1 to A2 is denoted by phi, and from A2 to A3 is denoted by psi. Suppose that this sequence is exact. Such a sequence is called a short exact sequence. Okay. Here, phi is a monomorphism or an injective map, and psi is an epimorphism or a surjective map. Psi is an epimorphism Okay, so in this case, let me erase the first two facts. In this case, phi image of phi is equal to kernel of psi, right? Since it's an exact sequence. So exactness yields phi of A1, which is the image of A1 under phi, is equal to kernel of psi. Since psi from A2 to A3 is a surjective homomorphism, homomorphism upon using the first isomorphism theorem for this homomorphism psi, one gets A2 modded out by kernel of psi is isomorphic to psi of A2, right? The image of A2 under psi of A2, that is A2 modded out by kernel of psi is phi of A1, and psi of A2 is A3 itself, since psi is surjective. This isomorphism is induced by this group homomorphism psi. Okay. Conversely, if psi from A to B is an epimorphism, with kernel K, okay, in other words, kernel of psi is K, then the following sequence 0 to K, and K is included in A, right? K is a subset of A, which is the kernel of this map psi, right? And from A to B is this map psi epimorphism surjective, and from B to the trivial group 0, this guy is exact. It's immediate because image of I, which is K, is kernel of psi, is exact, where I is the inclusion map. So this is what I'm writing here. Indeed, the image of the inclusion map, the image of K under the inclusion map is equal to K itself, which is equal to the kernel of psi. Okay, so that was the third fact. Okay, relative to exact sequence. Now the fourth fact is the following. Suppose the sequence A1 to A2 to A3 to A4, where the map between A1 and A2 is alpha, the map between A2 to A3 is phi, and the map between A3 to A4, from A3 to A4 is beta, is exact. Suppose that this sequence is exact, then the following are equivalent. First, alpha is an epimorphism. The second fact is that beta is a monomorphism. The third fact is that Phi is the zero homomorphism. So all elements of the group A2 are mapped to the identity element of A3. That's the zero homomorphism. Okay, good. Now, the fifth fact is again about this sequence. Suppose the following sequence is exact. Alpha is a map from A1 to A2, and then from A2 to A3 is a map, and then from A3 to A4, and from A4 to A5 is the homomorphism beta. Okay, so one thing is I need to mention here. I believe you are all familiar with this term from linear algebra. If F is a map from A to B, then co-kernel of F, which is denoted by coq F, is equal to B modded out by image of F. Okay, image of F is a, so if A and B are groups and F is a group homomorphism, then image of F is a subgroup of B, and co-kernel of F is defined as the quotient group of B quotiented out by the subgroup image of F. Okay, so suppose that this sequence is exact, then the following sequence is also exact. Then the following sequence is also exact. It's an easy exercise to prove. 0 to co-kernel of alpha to A3 to kernel of beta to 0. Okay, so this was the fifth fact. You need to prove it. Now, definition. We consider two sequences of groups and homomorphisms. Consider two sequences of groups and homomorphisms having the same index set. So both the sequences are indexed by the same indexing family or index set. Homomorphisms having the same index set. A homomorphism of the first sequence of the first sequence into the second. So what do we mean by a homomorphism between two sequences? So this is the first sequence and this is the second sequence. So it tells us that a homomorphism between two such sequences is a family of homomorphisms. Family of homomorphisms alpha I from AI to BI. Okay, so there is a homomorphism from A1 to B1, there is a homomorphism from A2 to B2, there is a homomorphism from A3 to B3, and the collection of all these homomorphisms is the family that we are talking about, and that is a homomorphism between these two sequences, such that it this family of homomorphisms need to satisfy further properties, okay, such that each square below commutes. Each square of maps AI to AI plus 1, okay, the first sequence, in the first sequence, and in the second sequence BI to BI plus 1, okay, and the homomorphism in the family from AI to BI is given by alpha I, and the homomorphism from AI plus 1 to BI plus 1 in this family of homomorphisms is denoted by alpha I plus 1, and we want this square of maps to commute. Each square of maps commutes. So when we call this an isomorphism between these two sequences, it is an isomorphism of sequences if each alpha I is an isomorphism. If each alpha I in the family of homomorphism is an isomorphism actually. Okay. So that's how we define isomorphism between two sequences. Okay, now let me give you an example of homomorphism between two sequences. Okay, so I have not introduced you to this concept of chain complex earlier. Let me do it now. Example is by means of chain complex and chain map. Okay, so chain complex plays the role of a sequence, and chain map plays the role of a homomorphism between two sequences. In other words, chain map is a homomorphism between two chain complexes. Okay, so what do we mean by chain complex? A chain complex, which we denote by calligraphic C, is a family okay. The first component is an abelian group, and the second component is a homomorphism, is a group homomorphism. Okay, so it's a family of abelian groups groups CP and group homomorphisms delta P from CP to CP minus 1, okay, indexed with integers. Such that del P composed with del P plus 1 is equal to 0 for all P. Okay, so let me write down the sequence. So here is CP plus 1, okay, an abelian group, and there is a group homomorphism delta P plus 1 which takes CP plus 1 to CP, and then there is a group homomorphism delta P that takes CP to CP minus 1 and goes on like that. Okay, now let calligraphic C is this family CP comma del P, and calligraphic C prime is the family CP prime del P prime. Let C and C prime be two chain complexes a chain map phi from this family calligraphic C to calligraphic C prime is a family of homomorphisms phi P okay from CP to CP prime, okay, such that delta P prime composed with phi P is equal to phi P minus 1 composed with delta P for all P. Okay. In other words, each of the following squares commutes. So let me draw these two sequences connected by the chain map. So here is the first sequence from CP plus 1 to CP to CP minus 1 and goes on like that. So this is delta P plus 1, this is delta P, and the bottom sequence or the chain complex is C prime P plus 1, C prime P to C prime P minus 1. Okay, so this is delta prime P plus 1, this is delta prime P. Okay, and this homomorphism is given by phi P plus 1, this is given by phi P, this is given by phi P minus 1. Okay, So I'll take a break now. I'll be back with the next segment in a while. Okay. Thank you for attending this third segment.